so let's try number 23 from 18.3, which I hope is an example of the fundamental theorem.
It is.
Right, so they give me a vector field f. It's y e to the xy I plus x e to the xy j plus cosine z k. And then they give me a curve. And they tell me the curve is a line from 0, 0 pi to 1, 1 pi. And a parabola, z is pi x squared in the plane y is 1. From 1, 1 pi to 3, 1, 9 pi.
Mm-hmm.
Right?
Yeah.
So the idea is someplace in 3-dimension land, right? I have 0, 0 pi. Oops, 0, 0 pi is up here.
2, 1, 1 pi.
Then we go over to 1, 1 pi, which is like back up here. We go along the line this way.
Then the parabola pi x squared.
And that's in the plane y is 1, right?
Yeah.
So that's a parabola parallel to the xz plane, right? And this thing ends someplace.
319 pi.
Yeah, so I've got 0, 0 pi here, goes to 1, 1 pi, and then we go to 3, 1, 9 pi. Okay, and someplace along this business, right, out in the world here, there's a vector field happening. And I'm wondering, right, if I make this little journey, does the vector field help me or not? Okay, so I have two approaches, right? One, I could parameterize both curves. Ick, right? But doable. I could differentiate both curves. I could evaluate and dot product and integrate from point A to point B, or from time A to time B, right? We could do all that. Or we could hope, right? Maybe that's the gradient of something, and I can just evaluate that something that this is the derivative of from here and subtract it, evaluate it from there. You guys see that? Mm-hmm. I'm kind of hoping, hey, maybe this is a terminal point B and this is a beginning point A, and I could just do f of B minus f of A. But it won't be this f, right? You guys see that? I'm hoping this is the derivative of something. Okay, so I'm wondering, right? Is there f of what?
X, Y, Z.
X, Y, and Z. How did you know it was going to be 3 variables?
Because there's three variables involved in gradient.
Yeah, because my gradient, right? The thing I'm hoping is a gradient, right? Is 3-dimensional. So I better have had 3 variables to take derivatives with respect to. You guys see that? So I'm wondering, is there an f with gradient of f is my vector field, capital F? So if there was, what would I know about f? Little f. Like, what does it mean for the gradient of f to be that thing?
That's path independent.
Good, it'll be path independent, but more.
It's a function.
Yeah, f's going to be a function, right? And what properties is that little f going to have?
Oh, f of b minus f of a.
Good, f of b minus f of a will be my answer. Right.
I know the df, dt, dx, like stuff like partials, and then
Yes. So
That
close.
was probably the exact order of it.
So if the gradient of my little f is this capital F, right? What does that tell you about y e to the xy?
Oh, that there.
Yeah, that better be the x partial,
Yeah.
right? So if there was, right, then the partial of f with respect to x would be y e to the xy.
Plus a constant function of z.
Well, yeah. So
Oh,
I haven't done that yet, but
later.
yeah, you're there.
Yeah, okay.
So this is what I would know about the first component. What would I know about the second component? Yeah, that should be partial of f with respect to y, right? So partial of f with respect to y, it better be
X e to the x.
x e to the xy, and the partial of f with respect to z better be
Cosine z. Cosine z.
cosine z, right? Okay, so out of this, I'm going to get 3 guesses for what my function f ought to look like. You guys see that? What's your first guess look like? f1. How do you get from knowing the x partial?
Integrate with respect to x.
Yeah, right? We're going to go, okay. I'm just going to slap an integral dx on both sides. And I'm going to get my guess for f, right? f1, well, f's probably almost, right? What?
E to the xy plus a constant.
E to the xy plus some constant.
Of yz.
And my constant is, right, a constant with respect to x. That means it could depend on y's and z's. You guys see that? Okay. What's your second guess going to be?
E to the xy plus a constant with respect to x, z.
Perfect. Good. And you got that by taking this second thing, right? And integrating the y, right? All right, so what's your third guess?
Negative sine z.
Negative sine z?
Yeah, plus a constant xy.
Negative sine z?
now
Integrating
sine.
cosine, so we should get sine.
Positive sine z.
Okay.
Right, I'm integrating cosine.
Okay.
So I'm wondering, what did I differentiate to get cosine? Sine is the. And then plus what?
Constant with respect to.
Constant 3, right? Which is not really constant, but it's constant with respect to z. So it can depend on
X,
x and y. Perfect. Cool. So what do you know about these? Like, these are your 3 guesses for f. Can you stick them together to make one cohesive function f?
Is this where I think we're building a triangle in one of the examples?
Oh, I don't know.
Like we did C1 plus C2 plus C3 equals.
Oh yeah, you can play that way. So there's some options for how you play this kind of balance game. And the one I like to do is just say, okay, so here I've got this constant thing, right, that depends on y and z, right? But these two, the x and y bits are the same, right? And these should be the same function, so these two things should be the same. Which tells me what about their dependence on x and y?
Z.
They don't depend on x.
Yeah, they can't depend on x and y, right? So I can remove the x and y out of this dependence. And then what do I learn about z?
They're constant.
Yeah, so these are e to the x y's plus some constant, well, some function of z, right?
Mm-hmm.
And then that has to be this third one.
Yeah.
So what you learn should be that these two guys, right, match that thing.
Yeah.
And this thing matches these two guys.
Yeah. And then their f becomes e to the xy plus sine z.
Perfect. So f then is e to the xy plus sine z.
And then just evaluate those from the endpoints.
Yeah, really I should also have both.
Plus a regular constant.
Yeah, there really should be a regular constant here, right?
They call it K.
Yeah. Do I care about it?
Take the definite integral.
Yeah, I'm taking a definite integral, so I don't care about that thing. But really, honestly, right, there should be a k here. Okay, so once I found my f that my vector field was a gradient of, I can finally finish this problem off, which is to say that the integral over the curve of the vector field dotted with dr, right, the line integral over the curve of my vector field, is what?
Is
Integral from 0, 0, 5, 3, 1.
no e to the xy plus sine z evaluated from.
Perfect. Is the function, right?
Evaluated from 0, 0 pi to 3, 1, 9 pi.
Awesome. Right? Evaluate it from the endpoints.
It just becomes e to the 4 plus 1.
Yeah, so in the end here, what do I get? I get
Like
e to the 3 plus sine of 9 pi,
Which is 0.
Yeah. 4 plus 1.
0,
Yes, sir.
minus
E.
e to the
0
0
plus sine. Sine
plus
pi,
sine of pi,
which is 0. So e to the 3 minus 1.
okay. This piece is 0, this is 1, so that looks like I got e cubed minus 1.
Yep. Which is
4, right?
What's that?
no 3 times.
Oh.
Yeah, it's x times y, so 3
Oh.
times 1.
Yeah, I thought it was 4 too.
Cool.
Yeah.
Barring arithmetic errors, okay. Or maybe trig function evaluation errors. Does that help a little bit?
Mm-hmm.
So did it matter that I took this line and then this parabola?
Couldn't you have just done 2 parts too?
Yeah, we could have
Broken
just
out.
done this in 2 bits, right?
Yeah.
Added them together.
But this, what we found, right, when we answered this question in the affirmative, right? We asked, was this the gradient of something? And then we said, oh, hey, yeah, it's the gradient of this function, f over here. What that means is that it doesn't care how you get from the beginning to the end. What's up, Jake?
So if we take, if we take the derivative of lowercase f, we'll get uppercase f?
If we take the gradient of lowercase f, right?
Oh, because
That's
it's
the only
partials,
sense in
it's
which a
partials.
derivative makes
Okay.
sense for this kind of thing, right?
Okay.
So I have to take all 3 partials, make a vector out of it, and yeah, I'm gonna get big F.
Okay.
I'm gonna get here, right? This is the partial of little f with respect to x, the partial of little f with respect to y, and the partial of little f with respect to z.
Okay.
Cool?